Lifting a crate. The mechanism shown in figure is used to raise a crate of supplies from a ship's hold. So we're raising this crate of supplies. The crate has total mass 50 kilograms. A rope is wrapped around a wooden cylinder that turns on a metal axle. The cylinder has radius 0.25 meters, that's this capital R here, and moment of inertia I, 2.9 kilograms meters square about the axle. The crate is suspended from the free end of the rope. One end of the axle pivots on frictionless bearings. A crank handle is attached to the other end. When the crank is turned, the end of the handle rotates about the axle in a vertical circle of radius 0.12 meters. The cylinder turns and the crate is raised. What magnitude of the force F applied tangentially to the rotating crank is required to raise the crate with an acceleration of 1.4 meters per second square? You can ignore the mass of the rope as well as the moments of inertia of the axle and the crank. Okay, so we're given this information that the tangential acceleration is to be the tangential acceleration A is 1.40 meters per second square, and that's equal to alpha times angular acceleration times r. So that means because the radius of the wooden cylinder was 0.25 meters, we obtain an angular acceleration of the wooden cylinder as 5.6 radians per second square. Okay, so that's basically the angular acceleration of this wooden cylinder. So if this is going up, then it's going to be in this direction. So it's going to be in the clockwise sense. Okay, and the moment of inertia of a uniform cylinder was considered in problem 9.8. It's mr squared over 2 here, and this actually numerical value is given in the problem. It is 2.9 kilograms meters squared. That's the moment of inertia for rotations about the central axis. The net torque on the cylinder is going to be equal to moment of inertia times alpha. Now the moment of inertia is 2.9 and alpha is 5.6 radians per second square. Now what is the direction of this alpha? You can see here, this is my x-axis, y-axis and z-axis. When I curl my fingers in the direction of alpha, my thumb points in minus I hat direction. So the torque is in minus I hat direction. So the net torque is 16.24 Newton meters in minus I hat direction. Now, if I concentrate on the free body diagram of this crate here, there's the weight of the crate and the tension acting on it. So you can see these two forces, and the net force on the y-axis should be equal to the tension minus the weight mg, which is equal to tension minus, it's a 50 kilogram crate times 9.8, and which is equal to mass times acceleration 50 times a, and that would be 50 times 1.4. So from this I can calculate the tension. 50 times 1.4 plus 50 times 9.8, 560 newtons is the tension acting on the crate. Now we need to concentrate on the torque on the cylinder. Now you can see that this tension is pointing down on the cylinder, and R cross T will give us a net torque in a torque due to tension in the I-hat direction. So this is going to be the application point of the force. So we start from the center, R cross T. So we point towards the application point, curl our fingers towards the tension, and the thumb points in plus I-hat direction. So if we calculate the torque acting on the cylinder, torque on the wooden cylinder here, there is a contribution coming from the tension. The net torque will have T times R times I hat contribution from the tension. And now there is a force here, tangential force being applied. So that's the perpendicular distance to the pivot point. So I point from the central axis towards the application point, curl my fingers towards F. I see that the torque it causes is in minus I hat direction, and that would be this R times F in minus I hat direction. So the torque I find is minus F R in I hat direction. So the tension I have calculated was 560 newtons. The radius was 0.25, so 560 0.25. I had minus force F times the crank, basically the radius of the vertical circle, that's the distance between the central axis and the force F, application point of force F, 0.12 meters. 0.12 I hat. This is equal to the net torque we have calculated 16.24 in minus I hat direction. So this equation gives us 156.24 is equal to 0.12 F. If we take F to the right hand side and minus 16.24 to the left hand side, and we find the force to be 1302, which is to be basically reported with two significant figures. That's the minimum number of significant figures here. So it has to be rounded to 1300 newtons when we report the final answer. Okay. Now, to summarize, we have a crate that we are lifting here. So the crate has a free body diagram which consists of the tension pointing up and its weight mg pointing down. And this is equal to the net force acting on it. So therefore it's mass times acceleration. Remember that this is a 50 kilogram crate. So 50 times A. This acceleration is given in the problem as 1.4. which allows us to calculate the tension acting on it. And this tension basically applies a torque on the cylinder, which is R times T, and using the right hand rule we see that the torque is in plus I hat direction. So we find this component TR I hat, and because the net torque acting on the cylinder is I alpha using Newton's second law rotational form. And where is the direction of alpha here? Because this crate is going up, this should be rotating in the clockwise sense. So the net torque should be in minus I hat direction. So I curl my fingers, right hand fingers in the direction of alpha. My thumb points in minus I hat direction. So that net torque will also have a contribution coming from this the force applied on the crank handle. The crank handle applies a torque lowercase r times F in minus I hat direction. Using the right hand rule, I point from the pivot to the application point of the force, curl my fingers four fingers towards the force, the thumb points in minus I hat direction. So then I see that this should be equal to the net torque that I calculate, I alpha. So from this equation, I can isolate F, and the end result is 1302. Then I was careful about significant figures. The minimum number of significant figures I have is 2, so this should be rounded to 1300 newtons as the final answer.